It's approximately 10 to the power of 100 years into the future. The last black hole in the universe has just evaporated, which means the universe has entered the dark era. The entire universe is cold, dark, and devoid of life. Everything is gone except a thin distribution of low-energy particles like photons, neutrinos, and electrons. There's no significant and meaningful energy source. As the lifeless universe expands, the remaining particles will continue to spread out so thin that interactions are virtually non-existent. Any interaction between particles becomes increasingly rare. There's almost zero chance of any complex structure formation due to lack of necessary energy differences, but given enough time, an inconceivably long time, in theory, regions of lower entropy could emerge, meaning particles organizing in certain regions and spontaneously form structures. Over time, the temperature of the universe gets closer and closer to absolute 0 Kelvin, a point beyond which there's no potential for further change, a state of maximum entropy or maximum disorder and randomness. This extremely slow process could take around 10 to the power of 100 to 10 to the power of 1,000 years, or even longer. The universe is now in a thermal equilibrium state, meaning no differences in temperature, hence zero energy flow. There's a uniform distribution of energy and matter throughout space-time. Without energy differences, no work can be done, and no events or processes can occur. This state is often referred to as heat death, where the universe is in a state of minimum energy with no large-scale structures or energetic processes occurring. At this point, it's reasonable to say that time as we know it effectively stops. Time, for humans, is often perceived through changes in events. It's measured by tracking sequences of events, like orbit of planets, galaxy rotations, or biological processes. In heat death, there's no observable changes, no events, no processes that we typically associate with the passage of time. In this sense, time would lose its practical meaning. While time as a dimension would still exist, the lack of observable change or events could be perceived as time stopping in an experiential sense. The universe is not only physically lifeless, but also devoid of meaning. There's no consciousness, thought, awareness, or purpose. The universe becomes pointless. However, even in a state of thermal equilibrium, quantum mechanics allows for the possibility of spontaneous quantum fluctuations, temporary changes in the amount of energy in space, as allowed by the uncertainty principle in quantum mechanics. Even in a vacuum, where you might expect there to be nothing at all, quantum fluctuations mean that there is always a buzz of activity at the smallest scale. According to this principle, it's impossible to know both the exact energy of a system and the exact time at which that energy is measured. This inherent uncertainty allows for brief, spontaneous changes in energy levels that aren't under any external influence. These changes can result in the temporary creation of particles and antiparticles in the vacuum. These particles pop in and out of existence in extremely short time scales, giving rise to what is known as a quantum fluctuation. In simpler terms, quantum fluctuations are the brief appearance and disappearance of energy and particles in otherwise empty space, caused by the underlying probabilistic nature of quantum mechanics. The dominant uniformity in energy distribution during heat death means that any fluctuation in energy or matter is purely random and can occur anywhere with equal probability. At this stage, there are no external forces or significant interactions driving the system towards a specific state. Quantum fluctuations can lead to very rare and localized deviations from equilibrium, resulting in sudden and unexpected production of ordered structures in small regions of the universe. After a mind-bendingly long time, the most extreme and bizarre structures could suddenly fluctuate into existence. like an isolated conscious brain in the middle of nowhere. This specific type of non-biological brain is known as Boltzmann brain. This fluctuated self-aware entity randomly formed out of the chaos by pure chance with false memories, sometimes with memories of having lived a full life. It thinks it's a person living in a world surrounded by others and the rest of human history. But that's just an illusion. Its mind is filled with experiences, but only because the fluctuation that brought it into existence implanted them instantaneously. That means every single neuron that's part of the fluctuation in that brain is in such a way that it perceives an existence like a normal human being. Its sense of identity, memories, and understanding of the world are not the result of a life lived or experiences gathered over time. The brain perceives itself as part of reality, yet this perceived reality is nothing more than a byproduct of its sudden and improbable creation. The vast world it senses around itself, every detail, every memory, are nothing but illusions popped up in the brief moment of its formation. Despite all of this, the brain's self-awareness feels utterly real to it. It has a consciousness, an awareness of itself as a thinking entity, but in reality, this consciousness is all there is. The people it believes to be around it, the history it thinks it's part of, and the knowledge it assumes it possesses are nothing more than illusions. There is no deeper reality supporting its beliefs, only the bleak, isolated existence of its awareness in an empty, meaningless, and indifferent universe. In a very long or infinite timeline, it's statistically guaranteed that some extreme fluctuations would produce Boltzmann brains. They could theoretically form at any point where there is a significant deviation from the average energy distribution of the universe. The probability of these fluctuations is inversely related to the size of the fluctuation. A brain with all the necessary neural configurations and memories requires an even more significant deviation from equilibrium, making their formation even more unlikely. The key point is that in a universe with the highest level of disorder or maximum entropy, rare and significant fluctuations become more probable, even though they are still incredibly unlikely. The exact probability calculation of such fluctuations would require a detailed model of the entropy and overall state of the high-entropy universe. Theoretically, in an equilibrium system, the probability of random fluctuations leading to simple structures is higher than that of more complex systems. However, as time progresses and all simpler fluctuations have already occurred, more complex structures, like Boltzmann brains, become the next most likely fluctuations to occur, although they're still extremely rare. The spontaneous formation of a Boltzmann brain is estimated to occur within a range of 10 to the power of 10 to the power of 50 to 10 to the power of 10 to the power of 120 years, starting from the point where the universe is in its final high entropy state. 10 to the power of 10 to the power of 50 years is a rough lower estimate, but still an astronomically long period for the time it might take for a Boltzmann brain to form. 10 to the power of 10 to the power of 120 years is a more conservative estimate, reflecting an even lower probability of such an event, given the complexity and size of a Boltzmann brain. These giant figures demonstrate just how rare and improbable such an event would be. The estimation relies on several critical factors, rooted in both physics and probability laws, including entropy, the second law of thermodynamics, the law that states in an isolated system, entropy or disorder tends to increase over time, reaching a maximum at heat death. Quantum fluctuations, the size and complexity of the Boltzmann brain, volume of available space-time. The more space and time there is, the more chances there are for quantum fluctuations to occur. Thermal equilibrium, the state to which the universe will transition during its heat death phase, where all regions of space are at the same temperature, very close or equal to absolute 0 Kelvin. probability and statistical mechanics, and the cosmological model of the universe, including its expansion rate and the nature of the vacuum itself, which influences how quantum fluctuations behave over time. Ludwig Boltzmann, the physicist who inspired the concept of Boltzmann brains, was very interested in the long-term fate of the universe. He argued that it's far more probable for a brain to come into existence by chance due to an extremely improbable low-entropy state, rather than the universe producing such a brain. The comparison here is between a fluctuation that results in a universe like ours and a fluctuation that results in a Boltzmann brain. While the Big Bang originated from an extremely small and dense region, the energy and conditions required to kickstart such cosmic event are immense. The amount of energy involved in creating the conditions for a new Big Bang, even from a tiny region, is vastly greater than what would be required for a much smaller, localized fluctuation like a Boltzmann brain. While the Big Bang might have started from a small region, the change in energy and entropy involved is so significant that the likelihood of its fluctuation is extraordinarily low. This led Boltzmann to conclude that it's statistically less likely for humans to have evolved naturally on Earth in a well-ordered universe than for a single brain to randomly fluctuate into existence with all the thoughts and perceptions we experience. This brain would believe it's a human in a structured universe, but in reality, it's just a temporary random fluctuation in a dark and meaningless universe that's already dead. What is the smallest and most probable fluctuation that could lead to a human-like observation of our universe? According to Boltzmann, it wouldn't be a whole universe in its evolution. It would be a brain, one whose neurons are arranged in such a way that it believes it's a living observer, capable of perceiving an enormous universe with stars, planets, and galaxies. Our human experience could be summed up as a network of neurons arranged in precisely the right configuration. We usually assume that these connections are the result of years of personal experience and millions of evolutionary years. If Boltzmann brains are more likely than the natural evolution of an ordered universe, then our perception of living in a structured, low-entropy universe is an illusion. Instead, we could be isolated brains in a high-entropy, boring universe, experiencing false memories and perceptions. What a horrifying idea. And here's the counter-argument. During Boltzmann's time, natural selection was not as widely accepted or understood as it is today. The integration of Charles Darwin's theory of natural selection into broader scientific thought was still in its early stages. Today, there's a clearer picture of how natural selection operates over long timescales. Natural selection explains how complexity can arise from simpler beginnings through gradual and progressive changes. The early universe, following the Big Bang, started with simple elements like hydrogen and helium. Over billions of years, these elements underwent a series of processes governed by natural laws, leading to the formation of more complex molecules and eventually to complex structures like the human brain. This process is radically different from the random fluctuations posited by Boltzmann. The precise and highly organized arrangement required for a Boltzmann brain to spontaneously emerge from a thermal fluctuation involves a level of improbability far greater than the gradual buildup of complexity through natural selection. Evolutionary biology demonstrates that while the initial conditions of the universe may have been simple, given enough time, a couple of billion years in the case of our universe and human beings within it, the development of complex life forms is a natural outcome of these processes. Think about the way a fractal, with its complex visual structure, can emerge from a simple mathematical formula. Similarly, a complex biological brain is far more likely to arise from evolutionary processes than from a random fluctuation. Natural selection allows for the gradual accumulation of small changes, each building upon the last, to produce highly ordered and complex life forms over extensive periods. This makes the emergence of a biological brain through evolution far more probable than the spontaneous appearance of a Boltzmann brain. Thus, with our expanded understanding of natural selection, it becomes clear that the complexity of biological organisms, including humans, is a plausible result of evolutionary processes rather than an unlikely fluctuation. The formation of a Boltzmann brain involves a sudden, highly specific arrangement of hundreds of billions of particles. The likelihood of such precise organization occurring by pure chance is incredibly low. In contrast, the universe began with the Big Bang, creating a relatively simple environment, and over billions of years, through natural laws and processes, these simple elements formed increasingly complex molecules, eventually leading to the development of DNA, sophisticated sensory systems, and the highly advanced human brain. So natural selection plays a crucial role here. Initially improbable events like the Big Bang set the stage for a sequence of evolutionary processes. Over long timescales, natural selection builds upon these initial improbabilities, leading to increasingly complex structures. Small, gradual changes accumulate, amplifying the original improbability into ever more complex life forms. So the emergence of complex ordered life forms is not as improbable as a single, spontaneous fluctuation, but is instead a result of a long evolutionary process. A Boltzmann brain, by its very nature, would be an incredibly short-lived entity. The idea of it surviving in any meaningful way is largely incompatible with the conditions under which it forms. The fluctuation that creates the Boltzmann brain would be just as likely to immediately disintegrate it. As an ordered structure popping into existence within a highly disordered environment, its survival would be extremely unstable with an incoherent consciousness. In a high entropy state, the brain would be bombarded by thermal noise, random interactions, and fluctuations that would rapidly disassemble its structure. Immediately after popping into existence, it would decay and die due to the absence of the necessary support systems and chemicals for its survival, and due to the overwhelming tendency of the universe of this specific era toward increasing entropy. Given that the brain is formed from a highly improbable fluctuation, it lacks any stability or support from its surrounding environment. Unlike biological organisms, a Boltzmann brain doesn't have systems in place to maintain its structure, regenerate, or interact with its environment in a sustained way. Its thoughts or consciousness would last only as long as the fluctuation that created it, which could be measured in incredibly brief moments, probably fractions of a second, or even much less. From the brain's perspective, it might experience a very brief span of time as a complete lifetime, given the nature of its formation. However, this would be a highly distorted, non-linear experience of time. A Boltzmann brain with a more durable configuration might, in theory, last longer than the typical brief moment associated with simpler kinds. This could involve a fluctuation that not only creates a brain, but also a temporary environment or structure that stabilizes it. The formation of these brains is already extremely improbable, and the probability decreases exponentially with their complexity and stability. A brain that could last for an extended period would be vastly more improbable than a short-lived one. The more complex and long-lasting a fluctuated brain is, the more it would resist the natural tendency towards entropy, meaning its existence would be constantly fighting against the surrounding chaos. In theory, an extremely rare fluctuation could create a brain with a complex internal structure that allows it to maintain its consciousness and possibly even perceive time in a coherent way for an extended period. This could be a scenario where the brain experiences life as we know it for a certain period and even interacts with a fabricated reality within its mind. Regardless of its complexity, Boltzmann brains would eventually decay due to the overwhelming thermal noise and lack of a stable environment. The longer it lasts, the more unlikely its initial formation would be. but it could still be a theoretical possibility in a gigantic universe with unlimited time. Does this mean that we might actually be Boltzmann brains? If we were Boltzmann brains, we wouldn't have the coherent and consistent experiences that we do. Any memories or perceptions of this type of brain would be illusory and not connected to any past or future. Our experiences are continuous and structured over time, which isn't in agreement with the nature of a fluctuated brain. We observe a universe full of complexity, with ongoing processes like star formation, galaxy evolution, and the development of life. These observations are consistent with a universe that is still far from maximum entropy. The complexity and coherence of our experiences suggest that we are the products of natural evolution, not random fluctuations. For a Boltzmann brain, the objective duration would be extremely short, probably a fraction of a second. But the subjective experience of time for conscious beings could be very different than objective, depending on cognitive processes and other factors. In a typical biological brain, assuming conscious experience is heavily dependent on the neural processes, self-awareness is sustained by ongoing neural activity and complex interactions among brain regions. In theory, it's conceivable that a Boltzmann brain could have a subjective experience that seems to last much longer than the brief objective duration of its existence. But its extremely brief existence poses challenges for sustaining any complex processes, including consciousness. The lack of coherence is the key issue. The rapid dissolution of the brain structure could disrupt any coherent experience it might attempt to simulate. It's been argued that if a Boltzmann brain formed with a highly organized and functional state, it might be capable of simulating a detailed and prolonged subjective experience, despite its very short objective existence. If subjective time is merely a construct of internal processes, then a sufficiently complex and coherent brain might be able to create a simulation of a lengthy experience. But of course, this experience would be entirely illusory, generated by the momentary neural configuration of the brain. And this is where it gets really weird and confusing. Assuming prolonged subjective experience of a fluctuated brain is possible, then how can we make sure that our observations of a coherent and structured universe aren't just an illusion? The reason the Boltzmann brain concept focuses on brains specifically is that a brain is considered the minimal physical structure required to support consciousness. The focus on brains rather than, let's say, a simple object like a rock is because the scenario is concerned with conscious entities that can question their own existence. If it's possible that most conscious observers in the universe are randomly fluctuated brains with false memories and perceptions, it raises the disturbing possibility that our own perceptions of a coherent, structured universe might be an illusion. Rocks, by contrast, don't have consciousness or perceptions, so they don't challenge our understanding of reality in the same way. The paradox comes up because a Boltzmann brain would have false memories and experiences, yet would still be able to question the nature of reality. If we were Boltzmann brains, we would have no reliable way of knowing it. Our entire perception of reality, including memories, sensory experiences, and logical reasoning, could be nothing more than random fluctuations. This makes the concept inherently paradoxical because it challenges our very foundation of knowledge, experience, understanding, and the nature of reality. If we are Boltzmann brains, our understanding of the universe, including the theory of Boltzmann brains itself, could be a delusion. If we're skeptical about whether we are biological or fluctuated brains, then we must question the validity of all our experiences. Even the possibility that our brains spontaneously formed with false memories and perceptions might make us distrust everything we know or perceive. This radical skepticism undermines the basis for scientific inquiry and philosophical reasoning and presents a deeply troubling paradox. Despite all of these, the paradoxes and philosophical implications of this concept are more relevant in theoretical debates than as a serious proposition about our actual nature. Our universe is seemingly fine-tuned for the existence of complex structures and long-lived beings, and to avoid the dominance of Boltzmann brains over biological ones. The conditions that support long-lived, coherent structures like galaxies, stars, and planets are more probable in our universe than random fluctuations leading to Boltzmann brains. Observations of cosmic background radiation, or the afterglow of the Big Bang, the distribution of galaxies, and the development of complex life on Earth support the idea of a stable and evolving universe. Our experiences and observations are not chaotic, inconsistent, or disjointed, as they would be if they resulted from random fluctuations rather than structured evolution, but they're coherent, stable, and aligned with the obedient universe we experience. The fact that we observe a universe full of stable, complex structures suggests that naturally evolved entities are far more common, and that the universe is not in a state of maximum entropy where Boltzmann brains would be more probable. Many cognitive scientists hold the view that consciousness is not merely a product of the brain in isolation, but rather emerges from the intricate and dynamic interactions between the brain and various other factors. These factors include the body's physiological processes, environmental stimuli, and social contexts. Consciousness is often viewed as an integrated system where the brain, body, and external environment work together to produce mental states. This approach contrasts with the notion of a Boltzmann brain that implies consciousness could spontaneously arise from a random fluctuation of particles without any such integration. Theoretical models of consciousness often emphasize the importance of specific physical and functional conditions for the emergence of mental states, and Boltzmann brain concept fails to meet these conditions. Boltzmann brain is primarily a theoretical construct used by physicists and cosmologists to explore the implications and test the coherence of different cosmological models. It also probes the limits of our understanding of the universe when it comes to entropy, heat death, and extremely long or infinite timescales. It's a thought experiment to question the assumptions we make about our universe. As an example, if a cosmological model predicts that the universe will continue existing for eternity after reaching heat death, then over that infinite period, these bizarre conscious entities, though extremely improbable in any given moment, could eventually outnumber naturally evolved brains, because there's an endless opportunity for them to emerge. This creates a paradox. Why do we observe a structured, low-entropy universe rather than chaotic, high-entropy surroundings? Because based on this conclusion, we should be living in a dead universe, and statistically speaking, be Boltzmann brains. This suggests that models predicting an eternal universe might need revision or may be incomplete, or that there are mechanisms in place that prevent the universe from persisting in a state where Boltzmann brains would dominate. The very nature of a Boltzmann brain conflicts with our intuitive understanding of reality, but it's also a logical conclusion coming from the principles of entropy and thermodynamic probability in an eternal universe. While the chances of a Boltzmann brain popping into existence are extremely low, the probabilistic nature of quantum mechanics gives it a non-zero chance. We and the entire universe could have been created just a second ago, and we wouldn't know, as long as the memories in our brains were consistent with our perception of the past. But we're not living in an era of the universe that can produce this type of brains. The universe's entropy has been increasing since the Big Bang for 13.8 billion years, but it's very far from its maximum. We're still in an era where stars are forming, galaxies are evolving, and complex structures like biological life can exist. There's much excitement ahead. The Boltzmann brain is an unfalsifiable hypothesis that can't be tested or verified. Science relies on observation, experimentation, and repeatability. However, if our very ability to observe and experiment is called into question by the possibility that we are Boltzmann brains, then the scientific method itself becomes unreliable. This creates a paradox where we can't even use the scientific tools to explore or understand the concept itself. It contradicts the scientific standards that require all hypotheses to be at least testable in a way that can be verified by multiple observers. The hypothesis must align with the majority of experimental and observational evidence, or, in other words, the bulk of this evidence doesn't contradict it. Other arguments supporting its possibility, like the infinity of time, fall outside the scope of physics, since they haven't been presented in a way that can be scientifically tested. The infinity of time is just a metaphysical notion put forward to support the argument. Even if you take the concept of very long time, it remains scientifically dubious and can't be taken seriously, as the term is indefinite and therefore can't be tested. Given that science currently has no means to investigate it, and because it contradicts the majority of experimental and observational evidence, scientists generally don't consider Boltzmann brain a serious scientific topic. But some cosmologists use it as a test or a factor to develop feasible cosmological models. It's a thought experiment created to probe some aspects of thermodynamics, entropy, and probability. It's one of the most mind-blowing consequences of physics, and its existence, generally speaking, shouldn't be taken seriously. It's typically regarded as a logical absurdity, an indication that there may be a flaw in our understanding of the universe's evolution. It's a concept for highlighting the limitations of extending the ideas like maximum entropy and quantum fluctuations to their extreme. The simplest way to prevent the emergence of Boltzmann brains is for the universe to have a literal end, so it doesn't last long enough for extremely low probability fluctuations like Boltzmann brains to become reality. But our current leading theories don't predict such an end. So, no matter how unlikely, we might be living in a universe that's just a fluctuation away from equilibrium, with entirely fabricated memories of the past. A sheer statistical anomaly in an endless, cold, and dark vastness of empty space-time, an anomaly of probability, an extraordinary assembly of particles that lasts for a brief moment before dissolving back into infinite emptiness.